Okay. All right. Here we go. Let's see what we got here. All right. Here we go. Anyway, it's another day, another week, right? Just came back from Florida. It was rainy and then it was nice weather. Anyway, see what we've got here. Um, yeah, the topic is time-light observations vindicated. That way I can get oriented as to what I'm talking about here. Just by way of a little bit of review here, we'll go with this. When we look into outer space, we're not seeing the same rates of time or the same measures of distance. As an example, we got some superluminal motion here, superluminal plasma jets streaming out from the centers of galaxies. Now, this is supposed to be pointed our way. Well, it is pointed our way because it's because of relativity. This jet beam is like in a thin stream here. But if you looked at the opposite end would be all spread out. But that's because of the effect of the gravitational lensing of this supermassive galaxy here, which is shooting out a stream of plasma, more or less not in our direction, but kind of in our direction. But notice the difference between the size of the jet here and the size of the jet here. Also, they measure the difference in speed here, somewhere here, and they got a measurement of 7 times the speed of light moving. And in other words, these clouds or plasma jets were moving at a speed 7 times the speed of light is what they measured. But they were projecting our measure of distance and our rate of time onto this area here from where we are inside of a galaxy. So we're inside of a galaxy trying to measure this out here, except we're not in this galaxy. We're in the Milky Way galaxy, but we're looking at another galaxy here, trying to measure something happening outside of this galaxy. This is clearly outside the galaxy, right? And if you notice, suppose if it was shooting straight across, right? Maybe, they would be equal or whatever. Maybe it'd be a better observation if it was shooting straight across. But anyways, but you can see how this size here is so much different than this size here, when in fact it's probably just about the same size. I mean, maybe it's spreading out a little bit, but it gives you the idea of a changing in the measure of distance here. In other words, this width here is a lot wider than this width over here. Regardless, because it's coming from the center of this galaxy, which is a point here. So the size of this plasma jet starts out as a point here inside the galaxy. And then as it moves away from the galaxy, this beam of light, which is basically what it is, a beam of light and plasma, is greatly expanded. And of course, it's moving at a faster rate of time. But anyways, that's just basically the the effect of general relativity has nothing to do with special relativity. It's just because special relativity has to do with things moving at the speed of light, which this is moving at the speed of light, but that's has nothing to do with our observation of light, because according to the light, light takes no time to travel no distance, which is nonsensical to us because we don't exist at the speed of light. Because we live in so slow motion, and everything we see is in slow motion. So this is what we see in slow motion. But it's the real effect has ramifications for how we see the universe, how we understand the universe. So, but the point is I've been getting some positive feedback. I just wanted to read some feedback that I got from, oops, wrong one. Where is it? I guess it's here somewhere. Yeah, it is. I'll figure it out. Don't worry. I'll figure it out. So, let me go over to this other window here, and I'll read the response here. And this is not the only response. This is just one response, but there's other ones I've gotten positive feedback from as well. And this one says, that is the best and most intelligent explanation of time and space and distance I have ever read. I have never accepted that light speed is the end-all speed limit for everything. Yeah, which is true with God. As a matter of fact, I mean, in reality, I mean, if you exist at the speed of light, time is exactly the way you explain it. I wish more people could understand everything you have said. You couldn't have put it a better way. It's perfect and to the point. You are one person I could talk hours about this. Which reminds me of a relative I have in South America that I enjoy discussing these things with him as well. But anyway, there's that, and let me see what else I can remember. But that is in reference to this here observation. There's also an observation of spiral arms moving faster than the speed of light. And there was an observation of when they hit an asteroid, they ran into an asteroid trying to knock it out of orbit, and they succeeded. But the asteroid was knocked out in such a way that it was moving faster than they expected it to move. And they're scratching their heads. Why is it moving faster? Probably wasn't moving much faster, but it was enough of a difference in the measure, the rate of time, and the measure of distance that they noticed that it was moving faster than they expected it to move. So extrapolate that out. Say we're here inside of a Milky Way galaxy, not this galaxy. This galaxy looks more massive than the Milky Way. But say we're inside next to a black hole, because which we are next to a black hole, because they just found out that we're closer to the center of the galaxy. So it's the entire mass of the galaxy that's contributing to the measure of time, the rate of time, and the measure of distance that we exist in. So compare that rate of time to out here. The rate of time out here is moving much faster, and this is still basically close to the mass of this galaxy, which is massive, but it's outside of this mass of this galaxy, but it's still close. Not to mention the distance between us and this galaxy. The distance between us and this galaxy is extreme, which is a little bit off topic, but the more you move out here, the faster the rate of time is going, and the more expanded the measure of distance is. So not only, which is important, because not only are things going at a faster rate of time, the distance isn't as far as what our predicted distance onto the universe is. Because this is not a single measure of distance. Let's say, for example, this distance here would be equivalent to this distance here, right? Which would be equivalent to this distance here. So the distance is getting expanded. So it's not actually not as far. So this distance from here to here is the same as from here to here, which is the same as from here to here. So our projected distance, which is basically this measure of distance here, we're projecting it onto here, and it's like 1, 2, 3, 4, 5, 6, 7, or whatever the comparison is, much larger than our distance here. So our measurement is about from here to here, say. So we're putting our measurement of that distance on here to here, when in reality the measurement is from here all the way to here, is what our measurement should be. So it's really not as far as what our projected measurement is, because our projected measurement is from here to here, when in fact it's from here all the way over to here, is the same measurement of expanded distance. So because our measuring stick, think of it as a measuring stick. This is our measurement stick over here, but when you get away from the mass of this galaxy, this measuring stick over here is going to be this big over here, and it's going to be this big over here. So imagine if you had a, I don't know why I'm thinking of Bigfoot, but anyway, you had a Bigfoot over here. You had a Bigfoot here, he's about this big over here. Then over here, he's about this big. And then over here, the Bigfoot is about this big. The same Bigfoot, he just moved out this way. So he's this big now. So that's, in reality, is what is happening. So it's actually less distance. The distance between our galaxy and this galaxy is not as great as what it appears to be. Because when you get out away from this galaxy, the distance is an expanded measure of distance. So it's actually not as far as what it appears to be. But since we're looking through space where there's no matter, nothing in between us, there's nothing in our line of sight between this galaxy and our telescopes. Nothing, no matter between us in our line of sight. That means that distance between us is not as great as what it appears to be. Because once the distance is going to expand between us, and then once it gets closer to our galaxy, then the distance is going to contract again, and back to this measurement over here. As a light from this galaxy moves towards us and reaches our detectors, our telescopes, and our eyes. So, but this distance over here from here to here is minute compared to the distance between this galaxy and our galaxy. So for most of the distance the light is traveling at an expanded, greatly expanded measure of distance, which it means it's not as far, and at a faster rate of time. So that's the reason why it can be, this galaxy can be, you know, millions of light years away from us. And even the redshifted galaxies that they found with the Webb, James Webb telescope, which is a pretty impressive instrument that they made. Even that distance of 13.8 billion years, light years, which is a distance, of course, and the distance, the time, it's a time and distance measurement. So that's 13.8 billion light years away, or almost, basically, because they're looking all the way almost to the beginning of the universe anyway. So it's about 13 billion light years away or whatever. That time and 6,000 years where we are inside of a galaxy is the same amount of time that passed. Only as the light was reaching our galaxy, it was traveling at a much faster rate of time through a less distance than what we measure it to be. So that's how we can see distant starlight or distant light from the most distant galaxies that are so far redshifted that we can't even see it. And it's so far redshifted that there's no evidence of anything, because anything beyond that would be completely redshifted outside of our James Webb potential to see it. The James Webb can see it because it's seeing the infrared wavelengths. But the other galaxy, if there's any more galaxies beyond what we're seeing, they're so much more redshifted that not even the James Webb is able to see it. So that's why they're not seeing any evidence of quote unquote dark matter, is because they're not seeing anything beyond the distant galaxies that James Webb is seeing anyways. So they would, even if there was galaxies out there, they wouldn't be seeing them because they're so far redshifted beyond the capabilities of James Webb telescope. But anyways, that's one of the things that the James Webb has been able to detect, which they didn't expect. Of course, they're backpedaling now and saying that, oh yeah, well, we'll just readjust our, interpretations or whatever, which is expected of them to do. But they still think that the universe is 13.8 billion years old because of the light, the time it takes for light to travel the distance to reach us. has to be at least 13 billion years. Except what they're not taking into account, of course, is the faster rate of time and the larger measure of distance. So let's say this is 1 light year. Well, it's not 1 light, it's more than 1 light year, but say it's whatever many, say it's 10 light years or whatever. Okay. That's the be over here. It'd be from here to here would be 10 light years, and over here it'd be from here to here is 10 light years. So the once it even leaves here, it's even more expanded. It's even at a faster rate of time and a more expanded measure of distance. In other words, it's the yardstick. It's a yardstick here. This size is the same as a yardstick this size, or a measuring stick, not a yardstick. Measuring stick this size and a measuring stick this size. They're all the same measurement. But to us, from where we are, they look like different distances when in fact it's the same distance. And the same thing with the rate of time. The rate of the passing time here, which, is the same here and here. So that not only is the time passing by faster where the photons travel to reach our galaxy, the distance is also much less than what we're thinking, or that what our measurement is. Our measurement is saying it's this distance here, when in fact the distance we think it is here is actually this distance here. So that's kind of a rough explanation of what the idea is that, is gaining some traction, which is a good thing. I'm getting some good feedback, comments, from more than one positive comment, But I just thought it would be good just to, highlight the comment that I had about the. I'll just read it one more time here. It says, which is, it's a pretty good comment, But I didn't pay him to say this, Even though it might seem like I paid him to say that, but anyways, he says, that is the best and most intelligent explanation of time and space and distance I have ever read. I have never accepted that light speed is the end-all speed limit for everything. Time is exactly the way you explain it. I wish more people could understand everything you have said. You couldn't have put it in a better way. It's perfect and to the point. You are one person I could talk to for hours about this, which is, it's very interesting. I mean, I could talk about this and many, many more things too, for that matter. But anyway, that's about it, I guess, for right now. Just a little review of basically the same thing. And, I guess I'll refrain from talking about genetic haplotypes and SNPs and geology for now. And since today is a work week, it's a work day, so maybe I should go to work. So God bless everybody. Take care and stay close to reality. Stay close to the truth, and the truth will set us all free. God bless everybody and take care.